This new unit is focusing on energy and chemical reactions. Specifically for this lesson, we're looking at energy, the basics of energy, and specific heat capacity. So the goals for this section, we're going to recognize and use the language of thermodynamics, so the system and its surroundings, exothermic and endothermic reactions, as well as describing the nature of energy transfers as heat, understanding the sign conventions of thermodynamics, and using specific heat capacity and calculations of energy transfers as heat involving temperature changes. So we can see the importance of energy and how it's evident in our everyday lives. For example, like heating and cooling our homes, powering the appliances that we use, allowing our vehicles to run to get us from place to place. And there's so many other ways that we use energy. Most of the energy we use for these purposes is obtained by carrying out chemical reactions, largely by burning fossil fuels. We use natural gas for heating, coal and natural gas to generate most of our electric power, and fuels derived from petroleum for automobiles and for heat. Energy is also required for living. Chemical reactions in our bodies provide the energy for body functions, for movement, and to maintain our body temperature. So we know that energy is the ability to do work, right? And that there's two main types of energy: kinetic energy and potential energy. Kinetic energy is the energy that's associated with motion, and we know that's 1/2 mv squared. We also know that potential energy is the energy that results from an object's position, its composition, its state. Well, we're focusing on thermal energy. Thermal energy is the kinetic energy of molecules. And thermal energy is associated with the transfer of energy as heat between a hotter object and a colder object. One type of potential energy is chemical energy, which is the energy associated with the forces holding atoms together as molecules or binding atoms and molecules together as solids and liquids. So in a chemical reaction, chemical energy, so potential energy, is converted to other forms of energy like heat or light, which is kinetic energy. So we've also talked about the law of conservation of energy. And we know that that says that energy cannot be created or destroyed. Whoops, I meant to underline this. So, stated a little bit differently, we can say that the total energy of the universe is constant. Now, in order to understand the importance of this law, we need to introduce some new terminology and carefully consider the implications of a number of different experiments. Now, when we get to doing problems here, looking at heat transfer, we symbolize heat as Q. So we'll be looking at Q and how to calculate heat in just a bit. We've also talked in previous lessons about the difference between extensive properties and intensive properties. So extensive property is a property that depends on the amount of material, like mass and volume. Mass is something, if I had a small piece of iron versus a large piece of iron, my mass varies. It's a property that depends on the amount. Volume, if I have a small glass of water versus a large glass of water, I have a small volume versus a large volume. That changes even though it's the same substance, right? If I had water, H2O, if I had 5 milliliters of it or 500 milliliters of it, that volume changes for water. Versus an intensive property is a property that is independent of the amount of material, like the density of water. The density of water is 1 grams per milliliter. If I had 5 milliliters of water, its density is still 1. If I had 500 milliliters of it, its density is still 1. So let's use that and talk about the difference between heat and temperature. Heat is the transfer of energy from a hotter to a colder object. This is an extensive property. If I have a much larger object, then there's going to be more heat transferred. So that is variable. Temperature is the measure of the intensity of heat, not the amount of it. So temperature is an intensive property. I could take the temperature of a small cup of boiling water that had 5 milliliters of water in it, and its temperature, if it's boiling, it's going to be 100 degrees. I could take the temperature of a huge pot of water, that's 500 milliliters of water, and it's also boiling, and its temperature is going to be 100 degrees. So both would have the same temperature, but there is different heat content because I have different amounts of it. So heat is an extensive property, temperature is an intensive property. In thermodynamics, the terms system and surroundings have precise and important meanings. A system is defined as an object, a collection of objects being studied. The surroundings include everything outside the system that can exchange energy or matter with the system. We will need to, in future references, we will need to define systems precisely. If we're studying the energy involved in a chemical reaction that's carried out, for example, the system might be defined as the reactants, the products, and the solvent. The surroundings would be the reaction flask and the air in the room and anything else in contact with the flask, which it might exchange energy or matter with. At the atomic level, a system could be a single atom or a molecule, and the surroundings would be the atoms or molecules in its vicinity. This concept of a system and its surroundings applies to non-chemical situations as well. To study the energy balance on our planet, we might choose to define Earth as the system and outer space as the surroundings. On a cosmic level, the solar system might be defined as the system being studied, and the rest of the galaxy would be the surroundings. So it's just important that how the system and its surroundings for each situation are defined depends on the information that we're trying to obtain or convey. Energy can be transferred between a system and its surroundings, or between different parts of the system. One way that energy can be transferred is as heat. Energy is transferred as heat if two objects at different temperatures are brought into contact. So we can see that the energy of the system can increase. So the energy of the system increases when heat is gained. So Q, we know, is heat. When it is gained, so that means that we have positive heat. So Q is greater than 0. When the system loses energy and the system decreases, that's because heat is lost. So Q is 0. So our Q is heat is negative. So Q is 0. So if the energy of the system decreases, that means that the energy of the surroundings increases. So we can say energy of SUR increases. And if the energy of the system increases, we know that it's because the energy of the surroundings has decreased. Energy transfer as heat will occur spontaneously from an object at a higher temperature to lower temperature. It always will go from the higher temperature to the lower temperature. The transfer of energy as heat continues until both objects are at the same temperature and thermal equilibrium is achieved. So it continues happening until they're at the same temperature. At thermal equilibrium, the object with a temperature increase has gained thermal energy. The object with a temperature decrease has lost thermal energy. We're going to do some problems to show that. But to describe those objects that are gaining and losing energy, we can see this. If I have an exothermic reaction, that means energy is transferred from the system to the surroundings. So energy of the system is decreasing right? Because energy is leaving the system, so it's decreasing for the system. The energy of the surroundings increases. So the Q of the system is less than 0. That means it's exothermic. An endothermic reaction, like ice melting, energy is transferred from the surroundings to the system. So my system is endothermic if Q is greater than 0, right? It takes heat, we can see this Bunsen burner flame, it takes heat from the system, is being added, from the surroundings, and is being added to the system. Therefore, this is an endothermic reaction. The energy of the system increases, the energy of the surrounding decreases. And to wrap up this section on energy and the basics of energy, we are going to look at energy units. So our main one that we use, the official SI unit of energy, is the joule. And the joule is equal to 1 kilogram meters squared per second squared. And actually joules, it's kind of like meters and kilometers. Joules, there could be a lot of joules in something. So we often, in chemistry, convert to the kilojoule. It's just easier unit since there's a lot of joules of energy. So kilojoules is just easier. We also can represent energy in calories, capital C, and little c calories. So 1 capital cal is equal to 1,000 calories, little calories. And 1 little calorie is equal to 4.184 joules. So this is just one conversion to go from English to metric, similar to if I said 1 inch is equal to how many centimeters. It's just an English to a metric conversion. We are used to using calories. That's how our nutrition facts are labeled. But in chemistry, in the metric system, we use joules. So let's just check that we can do conversions from one to the other. From calories into joules. So let's try this here. We've got 3.75 times 10 to the third. Little cals. And we want to get into joules. So that means, what do I want? Joules. What have I got? Little calories. And we saw in this slide right before that 1 little calorie is 4.184 joules. So in our calculator, we just need to do 3.75 times 10 to the third. 3.75 times 10 to the third times 4.184. And we know that these will cancel. We'll be left with joules, and we should get 15,606.32. Now, I started with 3 significant figures, so I would like to end with 3 significant figures. So we could either leave it as 15,600, make sure you put those placeholders zeros, or we can express this in kilojoules. And remember, there's 1,000 joules in a kilojoule. So we could also say, which is equal to 15.6 kilojoules. So either way works. So let's answer this question. Suppose we're studying a reaction occurring in a beaker on a table in the laboratory. What constitutes as the surroundings? The laboratory, the universe without the contents of the beaker, the whole universe, or the table? What do you think? If we're not being specific, then we need to just be like, well, it's everything but the beaker. Whoops. Which one of these processes is exothermic? A thermic lance, which burns rods of iron and magnesium and oxygen, generates enough heat to melt steel. An ice cube melting and cools a glass of warm lemonade. Evaporating sweat cools your skin. The sublimation of solid carbon dioxide, or dry ice. So dry ice coming from a gas, or from a solid to a gas. What do you think? Which one is exothermic? Where Q of the system is less than 0. The heat of the system is less than 0. Well, hopefully you said that it's generating enough heat to melt steel. We know that our system is losing heat. The surroundings is gaining it. It's obviously, the surroundings is gaining a lot of heat because it's enough to melt steel. Every one of those other examples would be endothermic. So let's move on to specific heat capacity. When an object is heated or cooled, the quantity of energy transferred depends on 3 things. The quantity of material, well, this is number 1, the magnitude of the temperature change, and the identity, including the phase, whether it's solid, liquid, gas, of the material. So, the size of the temperature change and the identity of the material. To mathematically relate the quantity of energy transferred to the quantity of material and the temperature change, we use the specific heat capacity. That's defined as the energy transferred as heat required to raise the temperature of 1 gram of a substance by 1 Kelvin, or by 1 degree Celsius. We know that the change in 1 degree Celsius is equal to the change of 1 Kelvin. So we can say either or. In like density, specific heat capacity is an intensive property. I could have a small amount of water or a huge amount of water, but the specific heat is constant. Here are some specific heat capacities of common materials, so things that we'll be using. We tend to, in our chemistry class, we really focus on the specific heat capacity that's in joules per gram Kelvin, or joules per gram degree Celsius. There are molar heat capacities, which is looking at the amount of energy transferred as heat in raising the temperature of 1 mole of a substance by 1 Kelvin. We will not be using that as much. For the most part, all of the questions that we will be dealing with is you're given 5 grams of copper, and so we would use our specific heat that's in joules per gram Kelvin. Getting into moles is just one more step. But so here, how do we find heat? Mathematically, the energy gained or lost as heat when a given mass of a substance is warmed or cooled can be calculated by Q equals, oh, actually, I don't like how this is set up. I like to say Q equals M times C times delta T. I mean, we know that multiplication is associative property, right? Where we can just flip-flop, but I like to say M times C times delta T, where M is the mass, C is our specific heat, delta T means the change in temperature. And when we're finding the change in temperature, we always do the final temperature minus the initial temperature. And that might not always be the bigger number minus the smaller number. If something is cooling down, let's say that my final temperature was 23 degrees Celsius, but my initial temperature was 40. I can have a negative delta T, and that's okay, all right? If I have a negative delta T times a positive specific heat times a positive mass, my Q will be negative, and that's okay. We want that. If our Q is negative, that's telling me that I have an exothermic reaction. It is giving off heat. So using that equation, Q equals M times C times delta T. We can use lowercase or capital, actually. Either, you'll see either. M times C times delta T. So we're given the specific heat of water as 4.184 joules per grams degrees Celsius, or joules per gram Kelvin. Again, either one, joules per gram degrees Celsius. So knowing this, I want you to try 3 different problems to see if you can solve. So this one, we're solving for Q, we're solving for energy. If 50 grams of water is warmed from 25.3 degrees Celsius to 33.7 degrees Celsius, what quantity of energy has been transferred to heat the water? So I want you to try this problem, pause, and I also want you to try 2 others, and we'll go over all at the same time. How much energy, so again, we're finding Q here again, must be transferred to raise the temperature of a cup of coffee from 20.5 degrees Celsius to 95.6 degrees Celsius. Assume that water and coffee have the same density and specific heat capacity. Okay. And the third one, you did an experiment in which you found that 59.8 joules was required to raise the temperature of 25 grams of ethylene glycol, which is a compound used as antifreeze in car engines, by 1 Kelvin. Calculate the specific heat capacity of ethylene glycol from these data. So see if you can solve those 3 problems, and then I'll check back in a minute. So when it comes to solving problems like this, I like to write down, what do I know? So I've got my Q, my M, my C, and my delta T. Let's see what we're given, because in order to solve for problems, we have to be given everything except for one piece of information. So it says if 50 grams of water, and I know that 50 grams is a unit of mass. There we go. And it says it's warmed from, so that means that my initial temperature was 25.3 degrees Celsius to, so the final temperature is 33.7 degrees Celsius. What quantity of energy has been transferred to heat the water? So my Q is question mark, which means we must be given C. And oh yeah, if we look up above, it says C for water is 4.184 joules per gram degrees Celsius. So let's find our delta T, our TF minus TI. So we're going to do 33.7 minus 25.3. Let's get that number here. I'm going to do 33.7 minus 25.3 to get 8.4 degrees Celsius. And that's a positive number. And a positive number is telling me that energy is being gained, right? If I had a negative, that would tell me that the energy of my system was decreasing. So I've got everything I need here to plug it into M times C times delta T. So Q is equal to 50 grams, my M, my C 4.184 joules per gram degrees Celsius, and delta T was 8.4 degrees Celsius. And if we look, we can see that all of our units are canceling, grams, grams, Celsius, Celsius, except joules, which is what our final answer will be in. So now we just need to plug and chug. So 50 times 4.184 times 8.4, and I get 1757.28 joules. Now we need to think about significant figures. We were given 3 for our temperature, 4 for the specific heat, and 1 for our mass, 50 grams. So I'm just wondering if it wants us to be specific to that 1. And actually our answer doesn't seem to care. So we can leave it as this full amount. We could also write this in kilojoules if we wanted to say 1.76 kilojoules, right? Move our decimal back 3 spots. So either one would work.